All right, so our last topic with aqueous equilibria involves going back to a topic that we talked about at the beginning of this course, but also something that we strongly talked about back in Gen Chem 1, and that is solubility. So back at the beginning of Gen Chem, we talked about solubility rules, like compounds with sodium ion are soluble and compounds with carbonate ion are not soluble. And these were general rules with a few exceptions. All right. Now we know that sodium chloride is soluble in water, but what happens if you put a liter of salt water in a pot, boil it until much of the water evaporates, and then cool it back down to room temperature? So, in words, what happens is that a salt will precipitate out when the concentration increases due to evaporation. So that means that we're exceeding the solubility limit. All right, now in an equation, after cooling, what we're seeing is that we got sodium ion, which is aqueous, and chlorine ion, which is aqueous, is forming sodium chloride, which we see as a solid. Now, at the beginning of this course, we talked about limits to solubility, and we can quantify the degree of solubility. So we talked about the units that you use. You could use grams per liter or grams per milliliter, and we can also quantify using molarity, moles per liter. But in addition to temperature, other factors can also affect solubility. So let's draw two pictures. One, in the first picture, let's draw a molecular image of silver 1 chloride, and remember low solubility. And then another one where we're adding seawater to the silver chloride. So here's our beaker, our first beaker. Okay. And I'm adding water. So I've got water in here. And at the bottom, and I'm going to make that silver chloride, I'm going to make that purple. And let's say we put a whole lot of silver chloride. Well, it doesn't really matter because it's got a low solubility limit, but you've got a lot of silver chloride sitting at the bottom, and you've got some silver ions in solution. You've got some chloride ions also. And I'll put another silver. Okay. But if we have, let's say we add another beaker, and this time we put the same amount of silver chloride in, okay, but we use salt water. So you're still going to have some silver chloride on the bottom, but a lot more of the silver chloride is going to be in solution. Now, you're also going to have sodium, you're going to have potassium ions, but you're going to have a whole ton of chloride ions. And that means you're going to have a whole lot of silver ions as well. Because okay. Now, why is this happening? Let's put a couple of sodiums in and potassium and all that. So, if seawater has sodium chloride in it, okay, and a whole lot of other stuff, and we're trying to dissolve silver chloride, what's going on? Why is the silver chloride being dissolved a lot more easier in seawater than previously? And it's because seawater, if we assume that seawater is just sodium chloride, because you have this chloride ion that's already present in the seawater, that's influencing how much silver chloride can actually be dissolved. So, what do we call the effect that would change the solubility of silver chloride in water? The common ion effect. Okay. The equilibrium between a particular solid and dissolved particles of the solid is chemically much like the acid base equilibria that we've been studying. So let's take a look at another equilibrium. This time, let's use silver 2 sulfate. So we've got Ag2SO4, which is a solid, and this is going to break down to form 2 moles of silver ion, okay, and we're going to release sulfate ion as well when it dissolves in water, okay. And if we give a description of the stoichiometry in words, what we're saying is that if we add Ag2SO4 to water, for every 1 mole of salt that dissolves, excuse me, 2 moles of silver ion and 1 mole of sulfate ion will be in solution. Now we can write an equilibrium expression for this reaction. So let's first start by writing a Kc. The Kc for this reaction would be something like this. Concentration of silver ion, because there's 2 of them, it's going to be squared, times the concentration of sulfate ions, divided by the concentration of Ag2SO4. Now, because Ag2SO4 is a solid, that means that the concentration is not changing. So we got to take that out, okay? And so we're left with just the numerator. Now, instead of calling this Kc, we're going to call this something else, and we call this Ksp for a solubility. Okay, so Ksp, or solubility product, is going to be equal to the concentration of silver ion squared times the concentration of sulfate ion. All right, so what component of this mixture is missing from this expression? Well, it's the Ag2SO4, the reactant, and it's because it's solid. Okay, now this equilibrium value will change with what factor? Temperature. All right, so what do we measure in order to determine K? We want to know the concentration of the saturated solution. If you have K from a table, what can you predict? The concentration of the saturated solution. Now, this one's tougher. If you have K, what else can you predict for mixtures? Well, we could predict the concentration that will produce a precipitate. We can also predict the effect of a common ion. And so what I mean by that is that, let's say if the concentration of chloride ion is high, then that means the concentration of silver ion will be lower. Okay. And so here's a certain table, and this is not a complete table. Then let me finish that. Then concentration of AgCl. Okay. Here's a table of Ksp values, and you're going to notice as you're looking through these tables, these are extremely low values compared to the Kas and Kbs that we were talking about. Let's try this problem out. Find the molar solubility of calcium fluoride. All right, so in order to set this up, in order to do this, we need to set up an equilibrium table, a nice table. So let's write the equation. So CaF2 is a solid. It forms an equilibrium when it's in water with calcium 2 plus, and you're going to have 2 moles of fluoride ion. Okay, so initially, you have no molar concentration of calcium 2 plus and the fluorine. The change, you know that the concentration of the calcium 2 plus is going to go up by a certain number x. concentration of fluorine is going to go up by 2x because there's 2 fluorines. So at equilibrium, the calcium 2 plus will be x, and the fluorines will be 2x. Okay, so with our KSP expression, KSP is going to be equal to the concentration of calcium 2 plus times the concentration of fluoride ion squared, because there's 2 of them. And according to this table, calcium fluoride, the KSP value is 3.5 times 10 to the minus 11th. Okay, so if I put in our x's now, x for calcium 2 plus, and then 2x squared for the fluorine, okay, let's simplify this a little bit. So 2x squared, that's like saying 2x times 2x. And so you've got x here. So that's equal to 3.5 times 10 to the minus 11th. So 2x times 2x is like saying 4x squared times x would give us 4x cubed is equal to 3.5 times 10 to the minus 11th. All right, so if I divide both sides by 4, x cubed is going to be equal to 3.5 times 10 to the minus 11th divided by 4, or equal 8.75 times 10 to the minus 12. And then we've got this x cubed. So what we're going to do is take the cube root of that value, 8.75 times 10 to the minus 12. And so that tells us that x is going to be 2.06 times 10 to the minus 4th molar. Okay, so what that tells us is that the concentration of calcium 2 plus in solution should be 2.06 times 10 to the minus 4th molar, and the calcium of concentration of fluorine ions, because it's going to be 2x, 2 times x, that will give us 4.2 times 10 to the minus 4th molar. All right, now which one is the smaller number? The calcium. So the solubility limit is 2.06 times 10 to the minus 4th molar, because everything's hinging on this. Once you get past that, it doesn't matter how much how much the fluorines can hold in solution, or how much the solution can hold fluorines in. You've already hit that limit with the calcium 2 plus ion. You're stuck. You're done. Okay, so in this sense, calcium 2 plus is the limiting species. So calcium 2 plus is limiting the smaller value. Okay, let's try another problem. All right, so let's say for a saturated solution of silver 1 sulfate in water, it was found that the concentration of sulfate ion is 0.014 molar. Okay, so if that's the concentration in water, that means if we've got 2 sulfates for every, or you got 2 silvers for every 1 sulfate, that means the concentration of silver ion should be 0.028 molar. We're just doubling it because you've got 2 silvers. All right. So if we look up the KSP for that compound, all right, Ag2SO4, it's going to be 1.2 times 10 to the minus 5th. All right, so here's our question. What will the concentrations be of silver ion and sulfate ion if solid silver sulfate is added to a solution that is 0.2 molar sodium sulfate? All right, so we got a common ion thing going on. All right, so initially, let's get an equation done. So you got Ag2SO4, which is your solid. It's dissolved in water, and you form 2 moles of silver ions, and you've got sulfate ion. Okay, so initially, you've got no silver, but you know that you've got 0.2 molar of sodium sulfate. So you know you've already got 0.2 molar sulfate in solution. Okay, so you know that the change the change in the silver ion has to go up by 2x, and the sulfate also has to go up by x. Okay, so at equilibrium, the silver is going to be 2x, and then the sulfate is going to be 0.20 plus x. Okay, so if I write a KSP expression, KSP is going to be equal to the concentration of silver, okay, because there's two of these silvers, we got to square it times the concentration of sulfate ion. And if we pop in our values, for silver, it's going to be 2x squared times the concentration of sulfate, that's going to be 0.20 plus x. And that's going to be equal to 1.2 times 10 to the minus fifth. Now, if we apply our approximation like we did for acid-base chemistry here, that means that this x over here in the 0.2 plus x part, we can ignore that x. The x is not going to be that much to change that value drastically. So we're going to get, if we apply the approximation, it now becomes this, that 2x squared, quantity 2x squared, times 0.20 is equal to 1.2 times 10 to the minus fifth. All right, so 2x times 2x should give us 4x squared times 0.20 is equal to 1.2 times 10 to the minus fifth. So if we multiply 4 times 0.2, that should give us 0.8. 80x squared is equal to 1.2 times 10 to the minus fifth. If we divide both sides by 0.8, that should give us x squared is equal to 1.5 times 10 to the minus fifth. And if we take the square root of that, x will be equal to the square root of 1.5 times 10 to the minus fifth, or that is 3.87 times 10 to the minus third. So that means that the concentration of silver ion should be 2 times x, or 7.75 times 10 to the minus third molar. And the concentration of sulfate ion should be 3.87 times 10 to the minus third molar plus 0.20. So it should be 0.203 molar. All right, so that means if we're looking at molar solubility, everything's hinging on the silver ion. Okay, now we can double check our values by popping our values into the KSP expression. So KSP, if we multiply our concentrations together, concentration of the silver ion was 7.75 times 10 to the minus third molar. And if we square that and then multiply it by the concentration of sulfate ion, which is 0.203 molar, it should come out to about 1.22 times 10 to the minus fifth, which is really close to what we had previously. Okay, so this graph that we're looking at is actually kind of explains a little bit more about the common ion effect. So on the y-axis, we're looking at the solubility of magnesium fluoride. On the x-axis, what we're looking at is the concentration of sodium fluoride. So as we keep adding more fluorine, more sodium fluoride to the mixture, what's going on is that the solubility of magnesium fluoride is decreasing, because as you keep adding more as you keep adding more sodium fluoride, you're getting to that point where you can't add as much magnesium fluoride. So as you keep adding more, as long as you keep adding a common ion, that is definitely affecting the solubility of as you keep increasing the concentration of sodium fluoride, you're decreasing the concentration or solubility of magnesium fluoride. All right, so on this graph, what we're looking at on the y-axis, we're looking at the solubility of calcium carbonate, and on the x-axis, we're looking at pH. Okay, and so on this graph, what we're looking at here is that at lower pH or higher concentrations of hydronium ion, Okay, we see that the solubility increases. All right, now is this an example of a common ion effect? And the answer is no, because H3O plus is not in calcium carbonate. Okay, give the chemical equilibrium for calcium carbonate dissolving in water. So that would be this: calcium carbonate, which is a solid, dissolves in water and forms calcium 2 plus ions and carbonate ion. Okay. Now carbonate ion, this is a weak base that reacts with the hydronium ion, H3O plus. And so if we look up the KSP for this salt, KSP would be about 5.0 times 10 to the minus 9. So in pure water, how would you characterize the solubility? Well, it's going to be pretty low. It's going to be really, really, really low. All right, so then give the chemical equilibrium that explains the shape of this figure above. What this would look like is that you got calcium carbonate as a solid plus H3O plus, which is aqueous, is going to be in equilibrium with hydrogen carbonate plus calcium 2 plus ion plus water. All right, so basically, if you want to think of it this way, H3O plus, again, that's water with an extra proton. In effect, what we're looking at here with this process, this is acid rain. So you got acid rain that's falling on buildings that are carved, or statues that are carved out of calcium carbonate. They're breaking down and releasing water, releasing calcium 2 plus, and releasing hydrogen carbonate. Okay, so does this figure make sense that as you lower the pH, the solubility is increasing? Absolutely it does. Absolutely it does. So does this figure make sense now? Yes, it sure does. And here's the moral of the story. The moral of the story is that solubility can be complex. Okay, so how can we generalize this phenomenon? So let's use some experimental results to help us make a generalized statement. And so we're going to look at this in two passes. The first pass is that we're going to look at salts with the following anions have solubilities that are not a function of pH. Okay, and if you remember, these are the anions that don't change pH. If you remember that list of when we were talking about the salts, when we were talking about ionic salts that have acid-base properties, these are the anions that have no effect on pH. So that list actually carries over here. Now we also have salts that with the following anions that have solubilities that are a function of pH. And so you have carbonate ion, you have cyanide ion, you have phosphate ion, and you have sulfide ion. Okay, so can you hear nature speaking to you? So let's see what the patterns are. So for part A, we're looking at anions that are ignorably weak bases. Okay, and then part B, what we're looking at is that anions that are not ignorable and they do react to neutralize acids. All right, now to be sure that you understand this concept, predict whether these salts are more soluble in acidic solution than pure water. So here's your two compounds, KOCl versus NaHSO4. All right, So let's take a look. K, we know is a cation that's in family 1A. That doesn't change the pH. That doesn't affect the pH, so we'll cross that out. Now OCl will react with water to give you HOCl plus OH minus. So this will make the pH greater than 7. All right. All right, so sodium ion, for the other one, sodium ion, family 1A, that doesn't change the pH. HSO4 minus, that can act as an acid or a base under certain circumstances, and that too will not have an effect on pH. So the one that we got to worry about is this first one, KOCl. All right, so you should be able to make many predictions based on the principle behind this chemistry. Okay. All right, so let's take a look at what nature is telling us. Let's check out this figure and the photo from the text. So here's our photo. We have a beaker that's filled with water, and at the bottom of this beaker, we have silver chloride. Okay, so it's quite insoluble in water, but if we add another compound like ammonia, it dissolves that silver chloride. Okay, so here was the solubility of silver chloride at pure water, but as we start adding more and more ammonia, that we do get an increase in solubility. So what's going on in words is that adding NH3 will increase the solubility of AgCl. Now, is this a common ion effect? No, because NH3 is not part of AgCl. Now, is this a weak base neutralization situation? No, again, because chloride ion is ignorable. Okay, so let's give the chemical equilibrium from AgCl dissolving in water. That was AgCl, which is solid, is going to form an equilibrium between Ag plus and Cl minus, both of these aqueous. Okay, and the KSP for this salt is going to be 1.8 times 10 to the minus 10. So in pure water, how would you characterize the solubility of silver chloride? Very low. Extremely low. Okay. So why does the solubility of AgCl increases as the concentration of NH3 increases? What we're doing is we're forming a complex ion. And to help us forming this complex ion, if we give the chemical equilibrium that explains what we're looking at Ag plus 2 moles of NH3, and this is going to be an equilibrium to form Ag parentheses NH3 2, and this is going to have an overall plus charge. All right, and if we were going to write an equilibrium constant for this reaction, the symbol that we would use is Kf, where Kf is formation of that complex. Okay, so if we use the two reactions to get a net reaction, you've got this: that AgCl forms an equilibrium between Ag plus and Cl minus, and then we've got Ag plus 2 NH3 forms an equilibrium to form Ag NH3 2 with a plus charge. All right, so Ag shows up on both sides of the equation. So if I add up these two equations together, we get AgCl plus 2NH3 forms an equilibrium with this complex, Ag NH3 parentheses 2 and Cl minus. To describe this, what we're talking about in words, we're saying that silver chloride can be dissolved by making a complex ion of silver ion with ammonia. Now, does this figure make sense? Yes, because now we understand why this solubility is increasing. We're making it complex. All right, so then it's saying if we rewrite the two component reactions, include all three equilibrium constants. So here's what we got. We got one reaction, AgCl forms the Ag plus and Cl minus. And the KSP for that reaction was 1.8 times 10 to the minus 10. The other reaction, you got silver ion plus 2 ammonia to form Ag NO3 NH3 2, and this is a plus charge. That ion, the KSP was 1.7 times 10 to the plus 7. If we add these two up, you get AgCl plus 2NH3 forms Ag NH3 2 plus charge plus Cl minus. And so adding up all these, if we multiply the two KSPs together, that should give us 3.1 times 10 to the minus 30. All right, so there it is. So one more thing to point out is sometimes that you can have more complications from nature. So for instance, here we're looking at the solubility of aluminum hydroxide, and it looks like aluminum hydroxide is pretty much insoluble from pH 4 to about pH 10. But as you decrease, you go lower than 4 or go higher than 10, you do increase it does increase the solubility. So aluminum hydroxide dissolves in strongly acidic solution as well as strongly basic solutions. So there is definitely things can get so the take home message here is that complex ion formation and complex ion solubility can get really, really complicated really quickly. So again, this is just enough to whet your appetites. If you go further on in the chemistry, especially inorganic chemistry, you will study a whole lot more of this stuff.